In the last section, we studied on orthogonal projection onto one-dimensional subspaces, lines. In this section, we'll generalize the orthogonal projection for general subspaces. See the recall. Given a non-zero vector u in Rn and y in Rn, we express y as the sum of y hat plus z. Y hat is parallel to u, and z is orthogonal to u. Y hat can be written as alpha u, and alpha can be determined by this quotient. And after getting y hat, we can decide z to be y minus y hat. The vector y hat is called the orthogonal projection of y onto u. Once L is the spanned line of u, then y hat, there's this vector, can be written in this way: projection of y onto L. And also this is orthogonal projection of y onto L. Now we will generalize the orthogonal projection. The theorem is called the orthogonal decomposition theorem. W is a subspace of Rn. Then y can be written uniquely in the form, and y hat plus z, and y hat is in W, and z is W pop. And if u1 to up is on orthogonal basis for W, then y hat, the projection of y onto W, can be written in this way. And after getting y hat, now z can be computed with this equation. And earlier you saw similar expressions when a subspace has an orthogonal basis. That's exactly like that. Here, okay, this is subspace W, and y is not on the subspace. Then y can be expressed as y hat, projection onto W, and an orthogonal component, that is z. So y hat plus z will become y. Okay. Let's try to solve problems. u1, u2 are chosen from R3, and y is in R3 here, and u1, u2 are orthogonal. We can easily check that. It's minus 4 plus 5 minus 1, so their dot product is 0, so they are orthogonal. And it can be on orthogonal basis for W if W is span of U and U2. Write Y as the sum of vector in W. That must be now y hat, the projection, and a vector orthogonal to W. That must be Z. Okay, let's try to do that. Okay, there's already part A begins with that way, and y hat must be given in this way. Okay, so that is now alpha 1, there's alpha 2. So here alpha 1 is y dot u1, u1 dot u1. So y dot u1, this is 2. Okay, let's try to write down the quantities. 2 plus 10 minus 3, and then u1 dot u1, there is 4, 25, and 1, so that must be 30. Right? Okay. y.u1 is 2, 10, minus 3. Okay. And now that is for 25 and 1 for the 30. And top is 9 and bottom is 10. Okay. So we say that there's 30 over 10. Okay. Now alpha 2, there's along with u2 we have to do it. Now that is minus 2 and plus 2 and plus 3 divided by, and u2 dot u2, 4 plus 1 plus 1, that is 6. So that is a half. Okay. So here y hat must be 3 over 10 u1 is 2, 5 minus 1, and now that is half, and u2 is minus 2 and 1 and 1. Okay, it can be considered as 5 over 10. So we put here 1 over 10, and then 3 is multiplied 6, and now there's minus 10, minus 4. This is 15 plus 5, so it's 20. And then there's minus 3 plus 5, that is 2. Okay. So that is, okay, let's try to use floating point values. So the minus 0.4 and 2 and 0.2. We can write in this way. Okay. Okay. Now here we can find the z, and that is here y minus y hat. Y is, okay, let's go over there. Y is 1, 2, 3. That is 1, 2, 3, and y hat is now that one, minus 0.4 and 2n 0.2. So that is now 1.24, that is 0, and this is final one is 2.8. Okay. Okay, now that's part A, and we have to find the distance from y to w. That is exactly the z. So we have to measure normal z. Okay. For this one, in fact, you can write this one in this way. There's 1.4 and 102. So that the normal z is same as 1.4, the coefficient, the constant, and that is now square root of 5. Okay. 1.4 times square root of 5. That's the answer. Okay. Properties of orthogonal decomposition. Y is decomposed into these two vectors, and w, okay, y hat is in w, and z is in w pop. Then y hat is called the orthogonal projection of y onto w, and we may use such a notation. And y hat is the closest point to y in w. That means that y minus y hat, of course that is a z. This is less than or equal to any the norm of norm with any v from w. So y hat is the closest point. See this figure. Y is there, then y hat is now projection onto the subspace, and y hat is nearest point to y. Also, y hat is called the best approximation to y by elements of W. And of course, if y is in W, then projection is not changed there. For second part, we can prove it easily. We choose an arbitrary vector v from W, then y minus v can be written in this way: y minus y hat and plus y hat minus v. Y minus y hat is orthogonal to W, but y hat is in W, and their combination must be in W. That is in W, that is in W pop. So by using the Pythagorean theorem, we can say the norm squared of that one is same as norm squared of this plus norm squared of that. That is the Pythagorean theorem. Now, if we try to compare these two, then this is always non-negative. That means that this must be at least this one. So this completes the proof. Find the closest point to y in the subspace now span of u1, u2, and hence find the distance from y to w. Okay. Now, once you want to use orthogonal projection, we have to check these two vectors are orthogonal. You can easily check that minus 4, minus 2, so that minus 4, minus 6, plus 6. So it is a 0 in dot product, so they are orthogonal. Now, we'll try to use formula, okay, and y must be here y hat plus z, but y hat must be here now y dot u1 and u1 dot u1 and u1 plus y dot u2 u2 dot u2 and u2 and plus c, right? Okay, that is alpha 1 and alpha 2. Okay, let's try to get alpha 1 and alpha 2. Okay, this alpha 1, there's alpha 2. Alpha 1 is, okay, y dot u1, that is 3 plus 2, so that 3, 5, 4, okay. It's a little bit complicated, so that let's try to write it. 3 plus 2 minus 1, and that is here, okay, 26, and u dot u1 dot u1, 1 plus 4 plus 1 plus 4, so that is 10. Okay, that is, top is 30, so it is a 3. Now, how about alpha 2? That is, this dot product is minus 12, minus 1, and 0, and plus 39. And then u2 dot u2, 16 plus 1 plus 9, so that will make 10 and 16, 26. Okay, also top makes 26, so that one is 1. So here, from here, y hat is the same as 3u1 plus now u2. You can get it quite easily. And after getting y hat, you can find the z, and z is y minus y hat, and the distance from y to w is norm over z. You can finish it yourself easily. Find the distance from y to the plane in R3 spanned by in u1, u2. This problem is essentially the same problem as the last example. Okay, anyway, here y must be now alpha 1 u1 plus alpha 2 u2 plus z. And that is y hat. Now alpha 1 is, okay, y dot u1 minus 15 plus 45 and plus 5 divided by u1 dot u1 and 9, 25, 1, so that is 35. Okay, that is 50 minus 15 is 35, so that is 1. Now alpha 2, okay, that is y dot u2 over u2 dot u2, right? Okay, so there's a minus 15 minus 18 and plus 5, right? Minus 15 minus 18 plus 5. Okay, now divide by, and 9, 4, 1, there's 14. Okay, there's a minus 10 along with this 5. So minus 28, which means there's minus 2. So we can get here y hat is same as u1 minus 2u2. Okay, let's get it. Okay, from u1 twice is subtracted, that means 3, twice subtracted, so that minus 9, right? That is twice subtracted and twice subtracted minus 1. Okay, that's y hat. And z will be y minus y hat. Okay, now y and y hat subtracted, then that is 2 and that is 0, and subtracted then 6. So that the distance is z norm, which is now square root of 4 plus 36, so that's square root of 40. That's the final answer. Okay. u1, u2, u3 are orthogonal bases for subspace W of R4, and V is in W. Okay. Now, by using u1, u2, u3, we can form a subspace W. Now, V itself is in W. Then V, we try to write V as a sum of two vectors, one in the span by u1, u2, and the other in u3, spanned by u3. Okay. So simply, you have to make here, now V is just a projection. Okay, projection of V onto, in fact, u1 and u2, let's say, write down in this way, and plus now projection of V onto here u3, like that, right? And you can write that way. And that problem is asking you simple projections. So for this portion, you can write in this way. Okay, that is V and u1 and u1 dot u1 u1 plus V dot u2 over u2 dot u2 u2, and that's this one, and this one must be here V dot u3 and u3 dot u3 and u3. If you find these vectors, and if you sum, then you'll see the summation must be of V. Okay, try it yourself. U1 to UP, the set of these vectors is on orthonormal basis for a subspace W of Rn, then the projection of vector y onto W can be written in this way. That's the formula. And right now, these vectors are orthonormal vectors. So length 1, originally, here we have on the bottom U1 dot U1, and over there we have U2 dot U2, and so on. However, this dot must be 1 because this is on orthonormal basis. So we ignore that, but this is just the formula. Right? Now, if we collect these basis vectors into a matrix U, then of course this matrix, because each column is orthonormal, so it has orthonormal columns, so that it will satisfy U transpose U equal identity. Now, this is not the result. Once we collect these vectors, then the projection can be written in this form, U transpose. Be careful, it's U transpose, not U transpose U, and can be written this way. And once it is true, we'll prove it here, the orthogonal projection, that projection can be viewed as a matrix transformation. This is a matrix, and projection is a kind of a matrix transformation. The matrix is made from the orthonormal basis of the space. Okay, look at this one. We look at that equation here, then each term, of course, these are scalars, constant, and it can be written in this way. That is same as U1 transpose Y, that is same as U2 transpose Y. Now, these values will make a vector in this way. That collection is the same as, in fact, U transpose Y. So here, and the remaining part is just U, and this is linear combination of the vectors U1 to UP, and linear combination of vectors can be written as metric vector computation. That is the fundamental idea in linear algebra. So we are using that, and we can reach that one. Now we look at this portion that is exactly a metric and transforming Y onto the subspace W. Okay. Y is 7 and 9, and U is given in this way, and W is span the space of U1. Okay, let U be 2 by 1 matrix whose only column is U1. Then we can compute U transpose U. Of course, U transpose U is now here 1 by 1 matrix, so that the value 1 will appear. And we'll try to get U transpose U transpose. Okay, so that is too simple, which must be 1. Number 1, in fact, is 1 by 1 matrix. Okay, now U transpose. Okay, that one. Okay, first of all, we'll rewrite U1 in this way, 1 over square root of 10, and here 1 and minus 3. And easier to handle. Now U itself is 1 over square root of 10, and that is 1 and minus 3. And then U transpose is Now 1 over square root of 10, the scalar, and row vector 1 and minus 3. We first multiply the coefficients, and then that will be 1 over 10. And then we form 2 by 2 matrix from this outer product. 1, 1 is 1. 1 and minus 3 must be minus 3. It's symmetric, so it must be here again, minus 3. Of course, that multiplication is minus 3, right? And this last one is 9. Okay. We get UU transpose. And in part B, we'll try to get projection by using the formula. And also, we'll try to get UU transpose Y. And in theorem, they must be the same. So the part B is asking you to check if they are the same. Okay, let's try to do the computation. Y dot U1 and U1. That is Y dot U1. Okay, that is 1 over square root of 10. And this dot product is 7 minus 27. So that here minus 20. Okay. And U1 is again 1 over square root of 10. And here that is 1 and minus 3. Okay. These two products will make 1 over 10. So whole thing over there is minus 2. So that, and that will make minus 2 and 6. Now, how about the other part? Okay, U transpose Y. U transpose is 1 over 10, and that is 1 and minus 3 and 9. And then Y is here 7, 9. Okay, we first write the coefficients 1 over 10, and then this product makes 7 minus 27 minus 20. That one will make minus 21 plus 81, so that 60. Now divided by 10 makes here minus 2 and 6. We see they are the same, right? So must be same. Mathematically, they must be same. Okay. Okay, now we reach at the true or false problems. If Z is orthogonal to U1, U2, and if W is a span of U and U2, then Z must be in W prop. That means that Z must be orthogonal to every vector in W. Is it true? Yeah, it must be true. And once you check if a vector is in W prop, subspace perpendicular, then you don't have to check every vector in W just by using spanning set. And if the vector is orthogonal to the spanning set, then it must be orthogonal to the spanned subspace. So it must be true. The orthogonal projection y hat of y onto a subspace W can sometimes depend on the orthogonal basis for W used to compute y hat. Okay. Part B is asking you if the projection can be different when you choose different orthogonal bases for a subspace. Is it true? No. It's always the same. The projection is unique, so that as far as the space is not changed, no matter how you choose the orthogonal bases, it doesn't matter always. the projection must be the same. So the statement is wrong. If the columns of an n by p matrix U are orthogonal, then U transpose Y is the orthogonal projection of Y onto the column space of U. Is it true? Yeah, we already, okay, this is a sort of a verbal statement for that theorem. Okay. Okay. If an n by p matrix U has orthonormal columns, then U transpose X equals X for all X in Rn. Is it true? That is projection, so that once X is, okay. Now, if we consider subspace spanned by columns of that U, then once X is in the column space of U, then it's not changing. However, if it is not in the subspace, then the projection must be different, right? So the given statement is wrong. Okay, that's the end of the section. Thank you.